Hi everyone, I'm Abhishek and I'm going to be presenting our paper Probing Emergent Semantics in Predictive Agents via Question Answering. This is joint work with my equal co-author Fede and other collaborators at DeepMind. So it's clear that we have made amazing progress in self-supervised representation learning over the past few years, spanning tasks across language, vision, reinforcement learning, and so on. In this work, we are specifically interested in self-supervised learning methods in reinforcement learning involving egocentric forward prediction, that is, predicting what future observations are going to look like. And specifically, our motivating question is how much objective or factual knowledge about the environment can an agent learn purely through egocentric forward prediction? To measure this knowledge, instead of analyzing activations or learning linear regressors for specific attributes, we use question answering. This makes our setup intuitive. We can simply ask an agent what it knows about its world and fairly open ended. It allows us to pose arbitrarily complex questions to an agent and get an answer back. Our experiments are conducted in this sort of an environment. So, this environment is Unity based. At every step, the agent gets access to an RGB first person observation, and it allows for a variety of objects in various colors and sizes to be placed at various parts of the environment. So it allows for quite a bit of procedural randomization. The agent has access to a few primitive actions that allow it to move around and look up, down, left, right. We train the agent for an exploration task that gives it a reward of +1 for going to an unvisited object, a reward of 0 for going to an object that it has visited before, and the rewards refresh once all objects in the environment have been visited at least once. On the left, I'm showing a top-down map visualization of what this reward structure looks like. Note that the top-down map is only for illustration purposes, and the agent only has access to first-person egocentric observations. Here I'm showing what sort of behavior the agent learns when trained this way from the agent's point of view. So these are first person observations. As you might expect, the agent runs around the room from one object to the next. For evaluation, we have a question answering task. So again, on the left, I'm showing a top-down map of the environment along with first-person observations at 2 points in the agent's trajectory. And the kind of questions we might ask the agent are, what is the color of the bed? How many wardrobes are there? What is the object near the bed? Is there a basketball in the room? And so on. Overall, we have several different question types. These vary in levels of complexity, and all of these questions are programmatically generated in a manner similar to Clever. So we have a few attribute questions that ask about shapes and colors. We have counting questions. We have existence questions that ask whether a certain shape exists in the environment or not. And then we have a few question types that require reasoning about multiple objects and their spatial relations. Importantly, this question answering evaluation is totally agnostic to the specific task that the agent is trained to optimize. So there's a stop gradient that prevents the gradients from this question answering decoder to be backpropagated to the agent. The idea being that as the agent explores the environment, it'll build internal representations, and we want to evaluate how good those internal representations are on this downstream task without backpropagating gradients. So overall, our pipeline looks something like the following. During training, the agent explores and learns to build representations purely from egocentric observations. We do this for a variety of different object configurations that are randomly generated. At evaluation time, the agent runs around in the environment, and as it builds up these internal representations, we evaluate how good these are on a question answering task. Moving on to the agent architecture, at every step, the agent gets access to first-person RGB observation. These get passed through a convolutional neural network to output a compressed vector. This vector is fed as input to the policy RNN, from which an agent predicts which action to take in the environment. And this continues at every step in an episode. Along with this, we have a predictive loss that operates on the hidden state of the policy RNN. We experiment with two choices of these auxiliary predictive losses. One is action-conditional contrastive predictive coding, and the other is SimCore. Both of these are fairly similar in that both of these involve action-conditioned forward prediction, so predicting a representation of what future observations are going to look like. Both of these are unrolled for multiple steps into the future, and these are purely self-supervised. So all of these observations and actions are coming from the trajectory that the agent traverses in this environment, and no labels were used. We also have a question answering decoder that I alluded to earlier. And crucially, there's a stop gradient between the question answering decoder and the hidden state of the RNNs. The gradients from question answering decoder are not backpropagated into the agent. Architecturally, the question answering decoder is fairly straightforward. We feed the hidden state of the policy RNN and words from the question into an LSTM to predict an answer. Moving on to baselines in Oracle, we first have a question-only baseline. So this agent does not have access to vision and tries to predict the answer only from the question. This baseline is useful to have to uncover biases in how the dataset was constructed. We then have an LSTM baseline that does not have any auxiliary predictive loss. For the predictive loss itself, we experiment with two choices, action-conditional CPC and SimCore. And finally, we have an oracle where we remove the stop gradient between the question answering decoder and the policy RNN. So this agent is trained end-to-end to move and simultaneously answer questions. So this setup, this oracle, is similar to prior work on embodied and interactive question answering. Moving on to results, here I'm showing the top 1 question answering accuracy on the vertical axis and the number of training steps on the horizontal axis. As you might expect, the no stop gradient oracle performs really well at this task and gets more than 90% accuracy. CPC, LSTM, and question only are close to chance performance, and SimCore gets about 70% accuracy on these shape questions. So it performs quite a bit better than action-conditional CPC and other baselines. If you look at results across all question types, once again, question only, LSTM, and action-conditional CPC are close to 30%. The no-stop gradient oracle gets about 63%, and the SimCore agent gets about 60%. Here are some qualitative visualizations. So here the ground truth question is, what is the aquamarine object? To which the answer is grinder. Starting from the top left in this visualization, I'm showing the first-person view of the agent, the top-down map of the environment, the answer probabilities as the agent runs around in this environment for this particular question, and the top 3 answer predictions. So as you can see, the agent begins with a fairly uniform distribution over answers when it's spawned in the environment. But as soon as it sees the aquamarine object, which is the grinder, it develops a fairly peaky distribution over answers, and it starts predicting the answer as grinder. And importantly, after seeing the grinder the first time round, as it moves to other objects, it retains that information in its internal state. So it is sort of building up this internal representation that it learns to retain internally. Here's another example. So the question is, how many blue objects are there? And the correct answer is 1. Once again, the agent starts with a fairly uniform belief over various answers, but as it spends more time in the environment, it becomes more and more confident that the answer is 1, as can be seen from the visualization in the bottom right. And here's one last visualization. So the question is, how many yellow objects are there? And the correct answer is 4. Once again, the agent starts with a fairly diffuse belief over answers, but as it spends more time in the environment and runs from one object to the other, it becomes more and more confident that the answer is either 3 or 4. So our environment supports quite a bit of procedural randomization, but it is still prone, the agent is still prone to overfitting. And to have a harder test for generalization, we develop these training and test splits where we hold out certain combinations of attributes seen during training for evaluation. And so the agent is not exposed to those combinations of attributes at training time. So for example, the agent may have seen questions such as what shape is the blue object, to which the answer is bed, and what shape is the green object, to which the answer is ball during training, but it has never seen what shape is the green object, to which the answer is bed at training time. Even on this compositionally novel split, we see that the SimCore agent is able to do quite well. which suggests that the internal representations that SimCore may be encouraging, they might be factorial to quite an extent. Another sort of post hoc analysis that this architecture allows us to do is to add another decoder to try and decode the entire top-down map from the internal state of the agent. So again, we have a stop gradient, and we don't backpropagate gradients from the top-down map prediction head into the agent. And this is sort of just a post hoc probe task that we evaluate the agent on. I'm showing the same example as before, along with the top-down map prediction on the top right. The ground truth top-down map is shown in the top middle, and as you can see, when the agent gets spawned in the environment, it does not know where various objects are placed, but as it spends time running from one object to the next, it develops a fairly good belief of where each of these objects are kept, what their colors are, and so on. And this sort of reinforces the high performance we saw of the SimCore agent on this question answering evaluation. So to conclude, we introduced question answering as a way to probe internal representations that agents develop as they perform tasks in environments. This probe task enables us to evaluate these representations using linguistic interactions, which is intuitive and fairly open-ended. Using this method, we evaluate several self-supervised predictive agents, and we find that methods such as SimCore are able to capture knowledge in a form that can be easily decoded into answers or facts about the environment, while non-predictive agents and action-conditional CPC do not lead to such representations. We also evaluate the SimCore agent on a compositionally novel split, and we see that the agent is able to do well on that split as well, which suggests that there might be some amount of compositionality in the internal representations that SimCore encourages. Our paper is publicly available, and please feel free to reach out to us if you have questions. That's it. Thank you.